application of X-ray absorption spectroscopy. It's my great honor to open up this SAS Journal Club as the first delegate of the Korean Society. Okay, I'll give a talk in this order. I'll give a very brief introduction about X-ray absorption spectroscopy, and I show you some examples showing the beauty and the power of the X-ray absorption spectroscopy to characterize nanostructured materials. And then I'll introduce our recent research activity. Actually, I'm a solid-state chemist, so we try to develop the novel material. We more focused on the synthesis of 2D inorganic nanosheet and applied them as a building block to build up the multifunctional hybrid material. So I'll show you some practical example of the nanostructured and hybrid material and the application of X-ray absorption spectroscopy to characterize these functional materials. As you know very well, the X-ray absorption spectroscopy is very, very powerful in material science and nanoscience. The SAS is the element selective, the highly reproducible is very important for me because like many others, we frequently use XPS to determine the bonding nature of the material, but the terribly not reproducible because the SAS data, XPS data can be easily modified by the condition of machine and the treatment of surface or something like this. So I love the SAS because they always give very, very reproducible data. And SAS is bulk sensitive, and we can effectively prove the local structure of specific element. And so it can give a very powerful tool to characterize nanostructured materials. So as you know very well, we can use the SAS information and XAS information from the genes. We can get the information about the oxidation state and the local geometry and chemical bonding nature. It's comparable to XPS, but as I told you before, then XPS is not so reproducible, but the XPS also has its unique merit, high sensitivity to surface. So if we combine both spectroscopy, we can selectively study the bonding state in the surface and in the bulk. Also, we can use XAS to determine the local structure of the materials. We can get the quantitative information about the bond distance and coordination numbers. Okay. So from the genes, we can get the information about the transition from the core level to unoccupied level. From the energy and the intensity of those peaks, we can get the valuable information about the oxidation state and bonding nature. And in XAS region, then photoexcited electron has sufficient energy to escape from the absorbing atom. So from the backscattering, we can get the valuable information about the local structures. This is selection rule for genes. So in the genes, we can have the formula for absorption coefficient. I want to emphasize the absorption coefficient is proportional to the density of the final state. So from the intensity, we can get the quantitative information about the density of the unoccupied electronic state. From the XAS, I think all of you are very familiar with this equation from the fitting analysis. Based on this equation, we can get the information about the coordination number and the bond distance and the Duval factor, reflecting the degree of disordering. I want to emphasize the amplitude of XAS is not simply proportional to the coordination number. It's also proportional to the amplitude reduction factors. It's somewhat tricky. So for exact determination of coordination number, we have to have the exact number for the atomic amplitude reduction factor. Normally, we determine the amplitude reduction factor for specific bonding pair from the well-defined reference data. That based on that, we can exactly determine the coordination number of the our materials. I love James because from the James spectral feature of James, we can get the many valuable data, valuable information. For instance, in KH James spectrum, there's a pre-edge peaks and the main edge peaks. From the pre-edge peaks, we can get the valuable information about the local structure of the metal ion in octahedral or tetrahedral. As you know, the intensity of the pre-edge peak is proportional to the structural distortion from the central symmetric octahedral symmetry. Also, from the position of pre-edge peak, we can determine the metal balance. Also, from the main edge peak, from the variation of peak intensity and position, we can get the information of crystal structure and the bonding nature and oxidation state. In case of L1H, we can see the transition from the 2s to unoccupied NP. So this transition normally give a very strong white line peak. So from the intensity of white line peaks, we can precisely determine the hole density in the final state of the NP state. Is very, very useful to determine the balance state of the halogen or chalcogen because they have the unoccupied state in NP state. In case of L2 and L3 James spectrums, core level, excited core level is 2p in those the edges. So in the James spectra, we can get the spectral feature correspond to the transition from 2p to ns or nd. So from that, we can get the information about the crystal field strengths and the hole density of this final ns and nd state. I know all of you are very familiar with this detection mode of James. I want to emphasize that we can use the X-ray detection mode and the electron detection mode. This is transmission and fluorescence mode detect the X-ray, but in total electron yield mode, we can detect the electron. Due to the strong interaction between the electron and matter, so in electron detection mode, we can get the information of surface, but in case of the X-ray, it has a much weaker interaction, so we can effectively prove the bulk species. So by combining them, then we can get the separate information about the chemical bonding nature in the bulk and surface. So the like the total electron yield mode, by using XPS, we can get the information about the surface bonding nature because with this spectroscopy, we measure the kinetic energy of the photoelectron. So if you combine the XPS and James in fluorescence mode or transmission mode, we can get the separate information of the bulk and the surface. Let me show you one example of the strong point of the combination of both James and XPS. We studied the bonding nature of the platinum ion stabilized in rutile TiO2 structures. From the James, we can get the very, very strong spectral similarity between the PtO2 and the PT substituted TiO2. So it is very strong point, strong evidence for the tetrahedral oxidation state of the substituted platinum ion. But if you study this material by using the XPS, as you can see here, we observe the coexistence of the platinum 4+ and 2+. So based on that, we can interpret this discrepancy as evidence for the stabilization of platinum 2+ on the surface. But in the bulk, substituted platinum ion is stabilized as a tetravalent state. Because on the surface there are many vacancies, so normally coordination number is lower than the 6. So as you know, the platinum 2+ can be stabilized in the square planar geometry or tetrahedral geometry due to the D8 electronic configuration. So it's very well matched with the general inorganic chemistry knowledge. So we frequently combine the XAS and Raman because the XAS can give a valuable information of coordination number and bond distance. Even though if you have a very nice XAS data for long distance, we can get the we can specify the crystal symmetry by fitting with the multiple scattering factor, but frequently it is not possible. But the Raman is very, very sensitive to the crystal symmetry. So if you combine both two, then you can specify the local crystal structure of the nanostructured materials. Let me show you one example. The long time ago, we synthesized amorphous manganese oxide nanocrystal as a lithium-ion electrode. We synthesized two kinds of the amorphous manganese oxide nanocrystal. We named as nano MnO2 and nano KW. So we confirmed the amorphous nature of those materials. So from the XRD, we can get any structural information about these materials. So we applied the X-ray absorption spectroscopy and Raman spectroscopy. So this is Raman KH James spectroscopy spectrum. So from the pre-edge peak, this is nano MnO2 is red line, and the green line represents the spectra for nano KW. So both materials shows very low the intensity for pre-edges. So this is the evidence for the stabilization of manganese ion in the octahedral symmetry. We were focused on the variation of the resonance peak, peak C. It is well known from the reference data that the intensity and the sharpness of this peak is proportional to the relative concentration of the edge sharing and the corner sharing of the MnO6 octahedral. In case of purely edge shared structure, we can observe very strong and sharp peak like the KW. But if the manganese oxide lattice possess the edge sharing and corner sharing, we normally observe much broader and the lower intensity peak C. So this is the case for the nano MnO2. So based on that, then we can presume that the local structure of nano MnO2 may be one of them, alpha MnO2, beta MnO2, and gamma MnO2, because those lattice composed of edge sharing and the corner sharing of the MnO6 octahedra. So in case of the nano KW, is the evidence for the presence of the edge sharing of the MnO6. So it must be due to correspond to the layered delta MnO2 and spinel type lambda MnO2 structure. So we do the XAS analysis. As you can see here, the first peak corresponds to the manganese oxygen bond, but there's a two distance share, the cross share. Second share corresponds to the edge sharing of the manganese bond distance. But the third peak corresponds to the corner shared Mn bonding pair. So in case of nano MnO2, as we guess from the genes, there's the edge sharing and corner sharing. In case of the nano KW, there's only one manganese peak correspond to the edge sharing. So based on that, we can guess the nano MnO2 composed of the edge sharing and corner sharing of the MnO6 octahedral. But in case of nano KW, composed of the edge sharing of the MnO6 octahedral. I already explained you that there are three types of the manganese oxide lattice containing the edge sharing and the corner sharing of the MnO6. But both each structure shows the different ratio of the edge sharing and corner sharing. Red line is just a simulation, it's not the fitted data, but without fitting, this shows the very well matching for the ratio between edge sharing and corner sharing, based on that we can successfully fit the experimental XAS spectrum of nano MnO2 as the alpha MnO2 structure. But problem is the nano KW, the XAS spectrum of this material can be fit with the edge sharing structure, but we cannot determine this structure correspond to the layer type or spinner type because both structure composed of the edge sharing. So we apply the Raman. This is the LiCO2 is the reference spectrum for layered metal oxide, but the LiMn2O4 is the reference spectrum for spinner. So if you compare the Raman feature, due to the amorphosity of this nanocrystal, Raman spectra is somewhat broad, but we can easily recognize this structure. The Raman spectral feature is more closer to the spectral feature of the LiCO2. So if you recreate these materials, we get the much clearer information for the spectral similarity between the layered phase and this nanostructured material. So by combining the Janes and Raman, so we can determine the local structure of nano KW correspond to the rhombohedral layered structures. Okay, let me move to our recent research activity. So as I told you in introduction section, we used the 2D nanostructured material, and we synthesized many 2D inorganic nanosheet, and we applied those materials as a building block to build up the hybrid materials. So it's quite similar to the graphene. It shows the extremely high anisotropy in crystal structure and morphology, but in contrast to the graphene, so it shows much greater diversity in chemical composition and structure. So we can enjoy the diverse tunable physicochemical properties and valuable functionality. So when we apply those materials as a building block to synthesize hybrid materials, so due to the very thin thickness of this materials, all the component ion are surface exposed. So if you combine this, if you couple this 2D nanosheet with the other nanostructured material, we can get the unusually strong electronic coupling. So by using this material as a building block, we can get the very unique, strongly coupled hybrid material. In that way, we can get many valuable functionality. Because we use those material as a building blocks, so we more focused on the synthesis of the monolayered inorganic nanosheet. There are three representative chemical routes to synthesize monolayered inorganic nanosheet. In case of layered double hydroxide and clay, those materials are highly swallowable. So if you soak those materials in appropriate the polar solvent, we can induce the infinite intercalation of solvent molecule. In the way we can get the monolayered LDH and clay nanosheet with the assistance of dissolution process. In case of layered transition metal oxide, there are exchange of the cationic species. So we can replace the interlayer ion with the bulky organic cation. In that way, we can minimize the interlayer interaction. Eventually, we can get the monolayered TMO nanosheet. In case of TMD, like molybdenum sulfide, there's no exchange of the interlayer, the ionic species. So at first, we have to intercalate the lithium ion by chemical or electrochemical way, and then react with water. In that way, we can induce the hydroxylation of the intercalated lithium ion. It leads to the evolution of the hydrogen gas. So it causes a drastic expansion of volume. So we can separate the TMD lattice into monolayered nanosheet. We can synthesize many kind of the inorganic nanosheet. We can somewhat tune the chemical composition by adapting the chemically substituted the host materials. Is the one of the example is very famous material for cathode for lithium-ion battery. We synthesized monolayered manganese nickel cobalt oxide by the intercalation-based exfoliation process. We can confirm the formation of monolayered nanosheet from the TEM and AFM analysis. One thing I want to emphasize is most of the inorganic nanosheet have sufficient charge, and most of them are negatively charged. One valuable exception is the LDH, because the LDH has the positive surface charge. So by exfoliating this material, we can get the cationic inorganic nanosheet, as you can see here. So based on their surface charge, we can easily apply the exfoliated inorganic nanosheet as a building block. We synthesize such a 2D hybrid material composed of inorganic nanostructures and inorganic polymer and inorganic organic moiety. Also, we can easily get the freestanding film by simple vacuum filtration of the colloidal suspension of exfoliated nanosheet. Also, we can apply the many kind of the deposition technique to get the inorganic film. We can apply the Langmuir Blodgett film to get the atomic layer, atomic thickness, the film. Also, we can get the deep coating or spin coating and electrophoretic deposition. Also, we can use those materials as a precursor to make the other type of nanostructured materials. We more focused on the energy application of those materials. We synthesized many photocatalysts for water splitting and N2 reduction and CO2 reduction and environmental purification. Also, we can synthesize many electrode material for metal ion battery, lithium sulfur, lithium oxygen, and supercapacitor. Also, we can synthesize many electrocatalyst material by using the 2D inorganic nanosheet. Also, we can synthesize the highly porous absorbent materials. Let me explain you several examples of the 2D nanosheet-based hybrid materials. Because those materials has a sufficient surface charge, we can use this material as a building block in terms of electrostatic interaction. For instance, we can induce the electrostatically induced self-assembly between inorganic nanosheet and the 0D inorganic nanoparticle or nanoclusters. So we can get the highly ordered intercalation structure or disordered and highly porous structures. Also, even we can the restack with the two different kind of 2D inorganic nanosheet, we can get the highly ordered superlattice structure or disordered porous structures. This is the first example of the 2D 0D system. So some old data, but I show you to show the advantage of the X-ray absorption spectroscopy to characterize such highly anisotropic materials. Previously, we synthesized the chromia pillared layer titanate by self-assembling between exfoliated titanate nanosheet and the positively charged chrome oxide clusters. But for application of gas absorbent, we have to maximize the microporosity of this material. So we catch up with the idea of the restacking with two different kind of nanocluster having different particle size. In that way, we can build up the robust pillar. So in that way, we can maximize the microporosity of this material. So we hybrid lead titanate with chrome oxide, the cluster, and cadmium oxide clusters. So we confirm the formation of layer by layer ordered structure from the cross-sectional TM analysis and the XRD analysis. Anyway, we confirm the formation of the intercalation structure from the powder XRD analysis as well. But from the XRD, we just observe 0 refraction, so we can get any structural information of titanate layer and intercolored the metal dioxide cluster. So we did the chrome KH chains analysis and cadmium KH chains analysis. From the chains analysis, we found out in edge prepared sample, the chrome oxide shows the highly confined nanoclusters, but during the heat treatment, it goes to the crystalline Cr2O3 structures, as you can see here. We observe distinct change in pre-etched spectrum. But in case of cadmium, the cadmium KH normally shows the featureless, broad spectral features. So from that, we can it is not easy to specify the local structure of cadmium from the James analysis. So we did the XAS analysis, as you can see here. This is the reference spectrum and the calcined sample at 500 degree. There's no significant structural change. So it shows the high stability, thermal stability of the cadmium oxide nanoclusters. The FT feature is very similar to the reference spectra of the cadmium oxide. Is the strong evidence for the stabilization of Luxor type CDO structures. Definitely, this FT structure is quite different from the chrome KH XF spectra. So from that, we can confirm the chrome ion just form the isolated chrome oxide non-cluster, not the substitute into the chrome site in chrome oxide nanoclusters. So we confirm the stabilization of the separated chrome oxide nanocluster and cadmium oxide nanocluster from the XAPS and James analysis. Also, by incorporating the cadmium oxide nanocluster, we can induce the microporous volume of these materials, as you can see here. So the resulting material shows the very nice CO2 absorbent the functionality. Also, it shows the high thermal stability, so it is comparable to MOF, but it's much more robust. Okay, let me move to the other example of the 2D hetero-layered hybrid. Yep.
Shall we accept some questions?
Yep, of course.
Okay, so audience, if you have any questions, so the mic on and ask him directly. So I have one question about your second topic. So what is the zero or the chromium 203 or cadmium oxygen, the nano cluster size?
Actually, this is not exact oxide, it's hydroxide. So we tune the pH of the precursor solution. So by precisely tuning the pH, we can induce the formation of the polynuclear cationic species. In case of chromia, maybe 4 metal cluster or something, and the cadmium case 2 or 3.
2 or 3. Oh, thank you. So then very small. So it is packed in the inside the layer.
Yeah, so that's the reason why I worry about the possibility of the chrome substitution into the cadmium substitution is the chromia nanocluster, because we start from the ion, not from the nanoparticle.
Yeah, thank you. So any other questions? No? Okay, so please continue.
Yeah, I see. Hold on. Okay. Okay. Let me resume.
Yes, please.
You can see. Oh. So we synthesized the many superlattice structure by using the oppositely charged inorganic nanosheet. This is one example. We synthesized the titanium oxide nanosheet is negatively charged. So as a counterpart, we synthesized cationic zinc chrome LDH nanosheet. So in the well-defined synthetic condition, we can induce the layer by layer ordering of the two kinds of the inorganic nanosheet. We confirm the formation of the artificial superlattice. It has the newly defined C lattice parameters, so we can confirm the formation of the artificial superlattice from the XRD analysis. As you can see here, the we observed the distinct low angle shift of 00L refraction. So this is the evidence for the formation of the layer by layer ordered superstructures. So calculate the lattice parameter is well matched with the summation of the uh, thickness of the each LDH layer and the titanate layers. We further confirm the formation of the superlattice structure from the cross-sectional TM analysis. Normally, those layers they listed each other for the 5 or 7 layers. So each highly anisotropic lead crystallite formed such a uh, house of card type the major porous structures. Also, we applied the Jane's analysis to confirm that the beauty of Jane's is the easy identification of the face because the even for the same tetravalent titanium oxide, each structure shows the unique Jane's spectral feature. It's the luteal structure, anatase, and the layered structures. So it is the very easily distinguishable. So the nanohybrid shows the typical spectral feature of the layer titanate. So from that, we can confirm the maintenance of the layer titanate lattice after hybridization. Also from KH and the zinc KH Jane spectral, we observe the typical spectral feature of the LDH. So from that, we can confirm the maintenance of zinc chrome LDH lattice after layer by layer order. So there's a many experimental evidence, but I skip it. But the resulting material shows the very promising visible light photocatalytic activity for the water oxidation. This is another type of 2D system. Even though molysulfide are neutral, but as I told you in introduction section, during the chemical exploration process, we intercalate the lithium ion into the molysulfide lattice. So it induced the partial reduction of the molysulfide. So as a result, the exfoliated molysulfide nanosheet are negatively charged. So we can easily apply those materials as a building block. We can synthesize the layer by layer ordered structure from the LDH and the molysulfide. We confirm the layer by layer ordered superlattice of the molysulfide and LDH from the XRD analysis and cross-sectional TM analysis. We also examine the Jane spectra. So the hybrid material shows the typical nickel and iron Jane spectra of the LDH. Also, in case of moly-KH, it shows the typical 1T prime molysulfide structure. So from that, we can confirm the maintenance of the nickel iron LDH lattice and 1T prime molysulfide structure after hybridization. So compared with the Janes, XPS is more sensitive to the interfacial charge transfer. So from the XPS analysis, we observed the slight charge transfer between molysulfide and LDH. It is confirmed by DFT. It's very noisy. There are a lot of thunder. Anyway, so from the DFT calculation, we can confirm the significant charge transfer and the LDH and molysulfide. Actually, electron migrate from the LDH to molysulfide. So It is valuable to enhance the OER activity of LDH and the HL activity of the monosulfide. Basic idea of this study is the synthesized bifunctional electro catalyst material, because the LDH is well-known OER catalyst and monosulfide is well-known HL catalyst. So as you can see here, such a layer-by-layer ordered hybridization is very effective in enhance the OER activity of LDH and the HL activity of the monosulfide. The resulting material can be effectively applied as catalyst for overall water splitting. We synthesize a lot of heterostructure, but as I told you in the introduction section, in LDH is the only cationic positively charged LDH inorganic nanosheet. So normally we adopt LDH nanosheet as a cationic component, but recently we found that the carbon nitride is very interesting and valuable building block, because we can tune the surface charge of the carbon nitride by tuning the pH of suspension. By lowering the pH of suspension, we can get the cationic carbon nitride nanosheet. So by using that, we synthesize hetero-layered structure by reassembling with the anionic monosulfide nanosheet. We can confirm the layer-by-layer ordering of the monolayered monosulfide and monolayered carbon nitride from the XRD analysis and cross-sectional TM analysis. From the Raman and the XAS analysis, we can confirm the transformation of monosulfide into 1T prime structures. So as you know, the 1T prime monosulfide is very effective to enhance the electrical conductivity and electrocatalytic activity of monosulfide compared with the pristine 2H structures. Also, we proved the formation of defect from the nitrogen 1s XPS analysis. So from that, we can confirm the increase of the nitrogen vacancy. So the hybridization can provide the effective tool to control the defect structure of the nanosheet. Also, from the DFT calculation, we confirm the occurrence of the distinct interfacial electron transfer from the carbon nitride to the monosulfide layers. We applied those material as a HL electrocatalyst, as you can see here. Compared with the pristine monosulfide, the resulting nanohybrid shows much better the electrocatalytic activity for HL reaction. Improvement of the reaction kinetics is confirmed by top slope calculation. Also from the impedance analysis, charge transfer kinetics can be remarkably improved by the hybridization. Also, the resulting material applied as a photocatalyst for anti-fixation. Anti-fixation gives the production of the ammonia. So as you can see here, the hybridization is very effective to enhance the anti-fixation reaction activity of the carbon nitride. From the isotope analysis, we confirmed the fixation of the atmosphere in the nitrogen into the ammonia. Actually, anti-fixation occurs by the photoreduction process. So the hydrogen generation is the competitive reaction to the anti-fixation, but in contrast to the anti-fixation, the hybridization leads to the suppression of the anti-generation. We believe that the main reason for the improvement of selectivity for anti-fixation is the generation of the nitrogen vacancy during the hybridization, because the formation of nitrogen vacancy is very effective in the enhancement of the absorption of the reactant anti-molecule to the catalyst. This is another type of the hybrid nanosheet. So in this study, we immobilized the major porous carbon layer on the exfoliated layered manganese oxide layer. nanosheet, as you can see here. We can confirm the formation of the sandwich type, the hybrid nanostructure from the XRD and TM analysis. And during such a deposition of major porous carbon, we believe that such a process induced the change of chemical bonding nature of local structures. Actually, for the application of the manganese oxide, the stabilization of the manganese 3 plus is very important because manganese 3 plus ion gives the very efficient reaction site for the OER process. But as you know, the manganese 3 plus is Yantala active ion. So in case of manganese 3 plus oxide, we can observe such a tetrahedral elongation, tetrahedral modification. But in case of the manganese tetravalent MnO6 octahedral, this is the regular octahedral. So in terms of bond distance, the equatorial bond distance of manganese 3 plus and oxygen is quite similar to the manganese 3 plus and oxygen bond distance. But due to the elongation of the axial, so axial manganese 3 plus oxygen bond distance is much longer than the other manganese oxygen bond distance. So to quantify the ratio between manganese 3 plus and manganese 4 plus, we can set up the model of this such a two manganese oxygen bonding shell that we can set as a manganese 4 plus oxygen and equatorial manganese 3 plus oxygen as the identical bond distance. But we can separate the axial manganese 3 plus oxygen bond distance. By using those cells, we can successfully fit the manganese KH absorption spectrum of these materials. As you can see here, as the content of the deposited carbon layer become larger, we observe the increase of the axial manganese 3 plus oxygen bond coordination number. So this is the evidence for the increase of the Yantala active manganese 3 plus species upon the deposition of the major porous carbon layer on the surface of manganese oxide nanosheet. So from that, we can confirm that we can stabilize the important manganese 3 plus species can be stabilized by the formation of layer by layer ordered sandwich structures. So we apply those materials as oxygen reduction electrocatalyst, as you can see here. We can confirm the enhancement of ORR catalyst activity. So we apply those materials cathode catalyst for oxygen, lithium oxygen battery, as you can see here. The hybrid material shows much better performance as an electrode for the lithium oxygen battery compared with the manganese oxide nanosheet, as you can see here. Also, we use the exfoliate manganese oxide nanosheet as a substrate to immobilize many kind of the nanostructured material and the inorganic species. This is one of the example for the anchoring of Prussian blue nanocrystal on the surface of manganese oxide. I want to emphasize that a lot of the surface exposed oxygen, it can act as a linker ligand to connect to the Prussian metal ion in Prussian blue lattice. Also, manganese ion is somewhat exposed to the surface, so there is another possibility of the linkage between the cyanide ligand and metal ion in the manganese oxide nanosheet. Anyway, we can confirm the formation of the homogeneous, the hybrid material between Prussian blue and the manganese oxide nanosheet from the TEM and the electrode diffraction and the XRD analysis. We proved the formation of the interfacial coordination bonding between the Prussian blue and manganese oxide nanosheet. From the iron and nickel and manganese KHF subs analysis, we confirmed the increase of the coordination number. It can regard it as evidence for the formation of the additional interfacial bonding between Prussian blue and the manganese oxide. Also, we use the Raman. So AB is the toner line correspond to the cyanide ligand. But if you replace the metal ion with the manganese oxide nanosheet, so interaction between manganese oxide nanosheet and cyanide become weakened. So it leads to the reinforcement of the cyanide bonding. So it is related to the change of the pi back donation. So as a result, we can observe the strengthening of the CN bonding. So as a result, we can observe the higher energy Raman peaks. Is the evidence for the coordination bonding between cyanide and the manganese ion in manganese oxide nanosheets. So by combining the XAS and Raman, we can confirm the formation of the bifunctional coordination bonding between Prussian blue and the manganese oxide nanosheet. Also, we apply those material as a supercapacitor electrode. As you can see here, we can confirm the significant enhancement of electrode performance upon the hybridization with the manganese oxide nanosheet. I want to emphasize the amount of manganese nanosheet is not that big, but the effect is very significant. As you can see here, such a hybridization is quite good to enhance the charge transfer kinetics of Prussian blues. Also, we do in situ Raman analysis. So as you can see here, to compare with the pristine Prussian blue, in case of manganese oxide hybrid, we observe the much stronger variation formation of the high energy peaks is related to the change of cyanide ligand, is related to the oxidation of the mangan the metal ions. So it's the evidence for the enhancement of the electrode activity of Prussian blue upon the hybridization of the manganese oxide nanosheet. Okay, let me move to other topic. Some sluggish. We try to control the defect structure of the nanosheet and hybrid. This is one of the example. We can synthesize the LDH nanosheet, and we list with the several representative anionic gas species. There's a significant change in size and charge density. We found out controlling of the charge density and size of gas species can allow to control the defect structure and the stacking thickness. So by lowering the charge density of the gas species, we can thinning the layer thickness of the least stack nanosheet. As you can see here, we confirm from the change of the XRD analysis intensity and the cross-sectional TM and AFM analysis. Also, we found out the reassembling with the larger inorganic species is effective to increase the defect level of the LDH. From the XAS and EPL analysis, we confirmed the increase of defect, anion defect. So it related to the enhancement of the elastic deformation of the LDH upon the restacking with the larger gas species. Is well correlated to the lattice strain of the LDH nanosheet. So due to the thinning and the formation of defect, so the reassembling with the bulk anionic species leads to the increase of surface area of the LDH nanosheet. So it's valuable to enhance the catalyst and electrode performance of the LDH nanosheet. We applied those restacked LDH as a OER catalyst, as you can see here. Restacking with the nitrate shows the much better performance than the LDH material restacked with the chloride ion. Also, we applied those material as a supercapacitor electrode. As you can see here, the reassembling with the nitrate ion also valuable to enhance the electrode performance of the LDH nanosheet. Actually, it's one of the best electrode performance of carbon-free LDH based material. From the correlation plot, we confirmed the crucial role of defect and stacking structure of the LDH in optimizing the electrocatalyst and electrode performance of the LDH material. From the defect calculation, we confirmed the increase of the interlace space leads to the increase of defect level, and the generated defect site can act as a electrocatalytically active site to enhance the OER catalytic activity. Okay. So also we try to tune the interface structure of the nanosheet and hybrid materials. Like many others, we synthesized many graphene-based hybrid material, but graphene is, even though graphene is a wonderful material as a hybridization matrix, but it suffers from several crucial demerits. One of the things is it suffers from strong self-stacking tendencies, so it is not to avoid the self-stacking of the LDH is definitely detrimental to the intimate coupling with the hybridized, the electronic coupling with the hybridized species. Also, basically, LDH is hydrophobic material, but the people try to couple with the inorganic solid, the most of the inorganic compound hydrophilic species, because it has a polar the chemical bond. So it's the intrinsic demerit of graphene. To overcome such a drawback of the graphene, we try to replace this graphene as hydrophilic and metallic inorganic nanosheet like the ruthenium oxide. Ruthenium oxide shows the high electrical conductivity and good stability, but there's no pi electron, so it is free from strong self-stacking tendency. Also, it has the polar chemical bonding, so it is good to get the strong electronic coupling and the interfacial chemical interaction with many kind of polar inorganic solid. We published a lot of paper about the merit of the hybridization with ruthenium oxide to enhance electronic photocatalytic activity and electrocatalytic activity and electrocatalytic activity of the inorganic nanostructures. It's one of the reason, one of the example. We hybrid ruthenium oxide nanosheet with the LDH. We synthesize the intimately coupled the hybrid material composed of the LDH and LUO2 nanosheet. We confirm the formation of the homogeneous hybrid material from the electron diffraction analysis. Also, we used the XAS analysis to change to prove the local structural variation during the hybridization. From the XAS analysis, we found out the defect formation occurs predominantly in the LDH, not for ruthenium oxide. I believe this is related to the lower lattice energy of the LDH, because in LDH lattice the hydroxide ligand is monovalent, and relatively the metal oxidation state lower than the metal oxide the nanosheet. So due to such a lower the lattice energy of the LDH during the hybridization, we can induce the oxygen defect in the LDH lattice. So we applied the resulting the hybrid material for OER catalyst and ORR catalyst. As you can see here, such an intimate coupling is effective to enhance the OER activity and the ORR activity. So we used as this material as the electrode for lithium oxygen battery. As you can see here, we observed the remarkable enhancement of the electrode performance of the LDH during the hybridization with the ruthenium oxide. To understand the advantageous effect of hybridization, we do the in situ SAS analysis during the electrocatalytic reaction. As you can see here, in case of ruthenium oxide, the application of electrical potential induced the migration of the absorption edges due to the charge accumulation. But in case of hybridization, hybrid material, there's no significant the change of the edge site is due to the efficient charge transfer in the intermittently coupled the nanosheet. Also, in case of iron KH and cobalt KH, compared with the pristine LDH material, we observed much weaker charge. The change of the edge site is due to the efficient electron injection into the reactant. So here's the evidence for the enhanced interfacial charge transfer between the catalyst and the reactant materials. Also, we applied the ruthenium oxide to boost up the photocurrent generated from the thylakoid. Thylakoid obtained from the vegetable like the spinach. Many people use the thylakoid to induce the photocurrent, but people did immobilize thylakoid on the surface of the gold substrate, but there is a limited electronic coupling. So to enhance the electronic interfacial coupling between the thylakoid and substrate, we introduced ruthenium oxide, because in ruthenium oxide nanosheet, there's a many sites for the cationic binding and anionic binding. So by incorporating ruthenium oxide nanosheet as an interlayer, so we observed the drastic enhancement of photocurrent, as you can see here. We fabricate the photosynthetic electrochemical cell. So as you can see here, compared with the ruthenium oxide nanosheet free cell, in case of ruthenium oxide based cell shows the much better performance as a photosynthetic photocurrent generation. Also, we do in situ XAS analysis. In case of the bare ruthenium oxide, we also observe the shift of the FT peak position is due to charge accumulation of ruthenium oxide. But in case of ruthenium oxide thylakoid hybrid system, we didn't observe the significant change of the FT peak position. Is the evidence for efficient interfacial electron injection from ruthenium oxide to the thylakoid. Okay, let me show you other example. We try to immobilize the selenite nanocluster on the surface of manganese oxide nanowire. As I told you, the stabilization of manganese 3+ is very important. But as I told you before, manganese 3+ can be stabilized as a tetragonally elongated the octahedral environment, because the manganese 3+ is Yantala active ion. So if you consider about the bond competition, so if you anchor the ruthenium selenite, highly oxidized selenite nanocluster, we can form the very strong selenite 6+ an oxygen bond. So it leads to the elongation of the neighboring manganese oxygen bond. So in that way, we can stabilize the Yantala active, the MnO6 octahedra. So we synthesize several the selenite anchored manganese oxide with the variable selenite content. We use the XAS analysis to confirm the formation of the isolated selenite nanocluster from the selenium XAS analysis, as you can see here. Also, the manganese oxide shows the typical active spectral feature of the alpha MnO2 structures. So like the case of sandwich, the carbon manganese oxide nanosheet case, we do the XAS splitting analysis by the two kinds of the manganese oxide shell is correspond to the manganese equatorial manganese oxygen bond distance and the manganese 4+ oxygen bond. Also, the axial elongated manganese 3+ oxygen shells. As you can see here, as the selenium content increases, we observe the increase of the coordination number of the axial manganese 3+ oxygen shell. So it's the evidence for the stabilization of the Yantala active manganese 3+ species. It is further confirmed by the XAS analysis, as you can see here. So we apply those material as ORR catalyst. So such as selenite anchoring is very, very effective to improve the overall catalytic activity of the manganese oxide nanowire. So we applied those materials as a cathode for lithium oxygen battery, as you can see here. Such a selenite anchoring is very, very effective to enhance the electrode performance of the manganese oxide nanowires. It's a similar the result. We stabilized highly oxidized iodate nanocluster on the surface of the manganese oxide nanosheet. So by using the XAS analysis, we confirmed the formation of the layered structures, even though some of the material shows the X-ray amorphous. So from the iodine L1H spectra, as I told you in the very beginning, the pre-H peak, the white line intensity is proportional to the density of unoccupied the iodine 5p state. So like the KiO3 pentavalent iodine, there are 6 the 5p holes. So intensity is similar to the reference KiO3. So this is the evidence for the stabilization of the pentavalent iodine species. Also from the XAS analysis, so we confirmed the stabilization of the Yantella active, the manganese 3+ oxygen octahedra. So resulting material shows the promising overall electrocatalytic activity and the electrode performance for the lithium oxygen battery. This is the final topic. So long. Okay. So we do the in situ XAS analysis to prove the effect of the cationic doping on the alpha MnO2 structure. From the lead belt analysis, we confirmed the vanadium substitution and iron substitution and cobalt substitution into the manganese site of the alpha MnO2 lattice. So from among those materials, the iron case shows the much promising performance as an OER catalyst. So we more focused on the operating mechanism of the alpha MnO2. We do the in situ XAS analysis, as you can see here. In case of the undoped one, there's a little change of the FD intensity, but it is not very significant. But in case of undoped one, we observed the significant improvement, enhancement of the FD peak, especially for such a corner shell. The increase of the peak intensity is much dramatic. So we believe this is due to the focusing effect in case of the collinear structure, such as the multi-ionic path shows the focusing effects in case of the collinear geometry. We observe such a remarkable enhancement of FD peak. So from that, we confirmed that during the OER process, in case of iron substituted one, the collinearity of the manganese O6 octahedra is improved. So it is definitely valuable to enhance the orbital overlap and the enhancement of the electrocatalytic activity. Also, it is valuable to improve the mass transfer properties. So it is confirmed by the impedance analysis. So based on that, we can suggest such an operation model for the beneficial effect of the iron substitution or the alpha MnO2. My talk is a little bit long, but anyway, let me conclude. We widely apply the X-ray absorption spectroscopy, especially in combination with the XPS and LAMA. So in the way we can easily characterize the poorly crystal material and highly anisotropic material and nanostructured hybrid material. So in terms of synthetic research, we applied the 2D inorganic nanosheet as a building block. We more focused on the engineering of defect structure and the interfacial structure. Okay, let me thanks to the organizing committee of the SAS Journal Club. Also, I specialized. I like to thanks to the Professor Sang-Woo Khan for the recommendation, and this is my collaborator, Professor Kim, Liu, and Choi, and my group member and the funding source. Thank you very much for your kind attention.
Thank you, Professor Hwang. So you are nice talk about the material and combination of nanomaterials that control the defect, and you can successfully characterize using XAS, TM, XRD, and Raman. So now the paper is open for questions and discussion. So anybody can switch on and ask him. So
I think my talk is too long, sorry.
So can I ask one question about your nano layer? So you make the superlattice,
Yep.
combining the two layer,
Yep.
different layers. So
Yep.
in that case, the interaction between them is electrostatic.
Static. Yep. Right.
So therefore, the AB, only AB is possible.
Yeah,
AAB
So
or some.
we also use the LBR technique, layer by layer deposition. So by using that, we can tune the stacking pattern with the several nanosheet.
Oh, I see.
We actually do ABC or ABC.
ABC.
Something like that. Yeah, right.
Like that.
Only for film, not for the composite.
Yeah. So another question is your last talk about the iron manganese. Yes, that one.
Yeah.
So you said that the collinear arrangement.
Yeah.
So in that case, some valence state changes or oxidation defect is created, then the arrangement of the iron manganese changes.
So actually, I did not do any theoretical calculation or something, but the iron is 3+.
Oh.
And in case of the alpha MnO2, the manganese has a mixed oxidation state, manganese 3+ and 4+. So by incorporating trivalent iron, so I believe that it lowered, no, I have evidence. It's lowering the content of manganese 3+. So because manganese 3+ is Yantella active, high level of the manganese 3+ induce some structural deformation. So I believe that's the reason why the iron substitution improved the structural ordering of the alpha MnO2 lattice.
So Yantella effect is the essential factor.
Yep. Right.
Oh, thank you. So any other questions? So please switch on. Yes, please.
May I ask a question?
Yes, please.
It's a bit related to what Asakura-sensei just said, what the manganese 3+ Yantella story. So I didn't fully understand. I mean, you do this anchoring of this selenium oxide, if I understand well. This distorts your structure, and thereby you said you choose to stabilize the Yantella.
Yeah, right.
But from my understanding, Yantella active means that there is a symmetric structure first, and then to the fact that you have manganese 3+, you get a spontaneous deformation of your octahedron. So this is not the same. I mean, if you take a chemical bond, then you distort the system chemically, and
kind
then,
of simultaneous.
This is no longer Yantella, is that?
The crystal growth of the alpha MnO2 lattice and the attachment of selenite nanocluster occurs at the same time. So there's actually two effects. The incorporation of such a high oxidation state leads to the lowering of the average manganese oxidation state. Also, in terms of the chemical bonding, selenium oxygen bond is much more covalent, much stronger than manganese oxygen. So in terms of the bond competition, so it leads to the weakening of the neighboring manganese oxygen bond distance. It leads to the elongation of the axial bond distance. So it's one of the contributing factors to stabilize the tetragonally distorted manganese oxide.
So,
Okay.
so the objective is to produce more Mn3 plus. That's the objective.
Yeah, right,
Okay,
right.
okay. Thank you.
So any other questions?
I may have a question.
Yeah, please.
Can you observe the interaction of the in plane of the film and out plane of the film?
Did you talk about the nanosheet? Or?
Yes, yes.
We can do with the film, the previously, especially for superconducting film, we do such an angle dependence experiment. But normally we do not. But there's one example. Okay, so in this study, I synthesized such a freestanding membrane by mixing the titanium oxide nanosheet and the graphene nanosheet. We can easily induce such a layer by layer ordering. So this is the Jane's spectra. So this is quite different from the powder pattern.
I see.
It's highly anisotropic. This such a spectral feature obtained from the highly oriented the deposited film. So from that we can get some information of the orientation of the nanosheet. Also by using the grazing angle mode, I believe that we can prove the outer bond bonding nature. Actually, I have the experience about this such a angle dependence, the SAS analysis.
Okay, thank you.
Okay, thank you.
Okay, any other questions? No more? Okay, thank you very much for Professor Hwang. Thank you very much.
Thank you very much. Thank you very much for your kind attention for such a
Yeah.
long talk.